Okay, students. So, after a break of yesterday, we're starting again. So, where we were day before yesterday, we were doing magnetic effects of current. Okay, and in that one, we completed magnetic field due to ring along its axis. Okay, now what we have to do? We have to find out magnetic field due to solenoid. Okay, so we'll start from solenoid now. Alright, and solenoid, what happens? What is solenoid basically? Now we all know that what is solenoid, but still we can say that it's basically a coil like this in which current flows, and because of current there will be magnetic field along its axis. Okay, you'll be finding magnetic field along its axis. What kind of magnetic field will be along its axis? Uniform magnetic field. There will be uniform magnetic field. Uniform magnetic field. Okay, this field is uniform. Yeah? Your voice is not audible. Okay, let me check. Is it okay? Yes, sir. Okay. So solenoid means is this kind of a coil is there in which current will be flowing. Okay, and we will be getting magnetic field along its axis. And what magnetic field? Uniform magnetic field. Okay, in this one there will be number of turns. More the number of turns are there, more stronger field we are going to get. Okay, so we will call that, if suppose we take these numbers are n. Okay, total number of turns n. Number of turns in coil. Okay, and we have its length. Say its length is L. Okay, its length is L. Then we define a number or number density, we call it as small n, which is number of turns per unit length. Number of turns per unit length. Okay, now how to find magnetic field in it? We use Ampere's law for that. And Ampere's law is what we have studied already. So what kind of Ampere's law we will be using in this one? Will it be circular like the other cases? Answer is no. Here we are going to use rectangular or square loop. Okay, because it's very long and we will be making a circle or rather Ampere's loop for very small section on it. Okay, so we have to make it in such a way so that it can cover up a certain number of turns which are carrying current, and it should also pass through the point where we want magnetic field. So where we want magnetic field? Along the axis. So axis should be there. So you'll be making one Ampere's loop. So Ampere's loop we are making like this. This is our Ampere's loop. Okay, this small. Now then, when you have made this Ampere's loop, you can see that here are the coils which are taking current and which are falling in this loop also. Okay, so how to do then? So we'll make another diagram over here to show that. Okay, right. So now this we have shown that this segment in which current is going inside. So current going inside or outside, anything we can take. Okay, so maybe we are taking it suppose inside. So inside current, this is current, okay, this is not magnetic field, this is current which is going inside. Okay, then Ampere's loop we will be making around it. This is Ampere's loop. This much or this much we have made. Okay, like this. Now what is the length of this Ampere's loop? We'll say dl. Okay, length of this is dl. It's very small. It's dl. And the current which is being carried over here is I. So here also this current which is going is I. Are you getting the sound? Students? because some disruption was there in the middle, right?
Yes, sir.
Okay, fine. So now these
They
are,
are not your screen in this business. They are not sharing your screen. Sir.
I have not shared my screen yet. Wait a
Yes, sir.
second, what's happening today? Hmm? Now?
Yes, sir.
Okay, okay. Let me check what's happening at the moment. 1 minute, okay? 1 minute. Okay. Everything seems to be good. Is everything clear? No problem, right?
No, sir.
Yeah. Okay. Okay. So let's start then. So as I was saying you that here is this small element we have taken whose length is dl, and you can see some of the wires which are inside this one. Okay, how many are there? We'll find it out, and how we are going to calculate magnetic field, we'll see. This is important actually because they may not ask us directly the magnetic field in the solenoid. They can ask you the magnetic field around a sheet. So this method is important for us. Okay, fine. So now what is Ampere's law? Ampere's law says that B dot dl. Okay, B dot dl equal to what? Mu naught I inside. Okay, B dot dl equal to mu naught I inside. Okay, fine. Magnetic field we want to know. Now we can see that because this current is inside, so in which direction magnetic field it is producing. So how to do it? We'll see that. Where is the current? We'll put thumb over there, and where we want the magnetic field, put your fingers like this. So palm gives you direction of magnetic field. That's what we have learned. So magnetic field here will be like this. Magnetic field will be like this. Then here magnetic field will come like this. Okay, like this will be putting. Okay, what about this? There is no magnetic field over here because this segment actually is here, or this segment is here, either here or here. Magnetic field is only along axis. That's what we are saying, uniform magnetic field. So magnetic field cannot be in this direction, magnetic field cannot be in this direction. Okay, so here all magnetic field is like this only. This is the direction of magnetic field. Okay, fine. So now what we are going to do? Let's apply the Ampere's law. Now how to apply? B dot dl we cannot write because here magnetic field is there, here magnetic field is not there, here magnetic field is 0. So how to do? Then we break it. In a breaking way we apply here. If suppose that I am going to take this as P, this is Q, this is M, and this is N. So B dot dl we'll write B dot dl for NP, then B dot dl for PQ, B dot dl for QM, B dot dl for MN. Like this we write B dot dl for entire loop. Okay, for every wire or every segment separately. That means like this. B dot dl. Suppose we are moving from N, so NP plus B dot dl from P to Q plus B dot dl from Q to M, and then B dot dl from M to N. Okay, we covered up entire loop. That's equal to what? Mu naught I inside. Now question is how much is I? Rather, how much is I inside? So we need to know that how many are number of turns. So we already have said that n is equal to number of turns per unit length. Okay. So how many turns will be there? We can say number of turns is equal to n into length of solenoid. So how much is length of solenoid we have considered? dl. So we'll write number of turns as n dl. So we'll write over here. There are how many number of turns are there? N dl. And each one is carrying how much current? I. So mu naught n dl into I. You return that. Done. Now what? We know that N to P, there is definitely magnetic field because of this wire. Is there? Okay. But this segment we have to see where it is. Shall we find it or not find it? So magnetic field outside the solenoid is considered to be 0. There is no magnetic field outside. Okay. Why it happens? Because see, I am at the moment considering only the lower section of the solenoid. But there is upper section of solenoid also. That is also producing magnetic field. Okay. So because this is also producing the magnetic field, so outside solenoid, magnetic field produced by the upper section plus magnetic field produced by the lower section, they cancel each other here. So net magnetic field here becomes 0. Exactly same way, this lower magnetic field, this lower section produce magnetic field here, and this also produce magnetic field here. So here both becomes in opposite direction, here also it becomes 0. But at the center only, the magnetic field because of the upper section and lower section comes out to be in same direction and they get added. Okay, so there are two ways to solve it. Solve it for lower section also, solve it for upper section also and then add. Or solve it for lower section itself or upper section itself and consider that outside magnetic field is 0, then we will be getting our answer directly. Then you don't have to do it twice. So I am using the second method only, in which I am going to consider that outside magnetic field is 0. Okay. So in solenoid, magnetic field outside is 0. Magnetic field outside is 0. Okay, fine. So now what? Let's see that NP. Now NP section means is here. That is outside. So magnetic field here is 0. So forget it. Okay. So 0 plus B dot dl PQ. Now in this one also, magnetic field is in which direction? Like this. In this way. And dl you are moving like this. So angle between magnetic field and dl is what? 90. And here is dot product. So B dl cos 90. Again 0. So this is also 0. Plus B dot dl qm. Now magnetic field is also like this. dl is also like this. So cos 0. So we can write this as B dl only. There is no problem. Okay, Nm. Here also magnetic field like this. dl is like this. That means again angle is 90. So again 0. Equal to what? Mu naught n dl into I. Okay, now you can see that this dl and this dl gets cancelled. So we are getting magnetic field inside the solenoid as mu naught Ni. Mu naught Ni, where n is number of turns per unit length and I is current. N is number of turns per unit length. So magnetic field for a solenoid that we have got is mu naught Ni, and this formula is important for us. Mu naught Ni. Okay, now based on this, I told you that it's important for us to know the derivation part. Okay, so based on this, if we can solve any problem, okay, what type of problem will be asked? As I said, sheet is possible. Okay, so suppose that one sheet is given to us. Sheet is like this. Okay. Sheet is like this. Okay. Like this sheet is given. Okay. All right. Now in this sheet, there are wires. We know that there will be infinite wires. Okay, these are wires, and these wires are actually carrying current. Okay, so current is going like this from one side to the other side. These are carrying current. Okay, now if the same thing I show you in a different way, suppose the sheet is shown to you like this. Okay, now in this one these are carrying the current. These are wires. Okay, these are wires which are carrying the current. How much each wire is carrying current I? Each wire is carrying current I. Okay, and now it is asked from you, find the magnetic field just outside this sheet. Okay, just outside. Maybe somewhere here. Okay, somewhere here or somewhere here I can make. Very close to this. Or in this case, if I have to make like this. Here we want magnetic field at point P. Okay, we may take this distance as d, but this distance d is very small. Right, then length of this sheet will be given to us. Okay, take it as L. And it will be given to you that how many wires are there per unit length. Okay, because there will be wires. So suppose n wires, there are n wires. In a sheet. So what is he saying? Total number of wires are n and total length is L. So again, if small n I want, I will be writing it as capital N by L. Right? Okay. Now what to do? Make Ampere's law, Ampere's loop. Okay. So here is Ampere's loop which passes through this point. Something like this we have made. Okay. Now remember that this is not solenoid. So if this is not solenoid, what is the meaning of that? Its meaning is in this one I am not going to consider here field is 0 and here field is not 0. Okay, in this one there will be field on both sides. Okay, here also field is there, here also field is there. Clear? So field is here also, field is here also. Now name them. Let's say PQMN again. This is P, this is Q. Oh, P already I have taken. Okay, fine. So in place of P, we'll be writing ABCD. So this is A, this is B, this is C, and this is B. Now move as we want. Okay, the way we want. We want to move from A to B, B to C, C to D, or you want to move A, D, C, B, it's your wish. Okay, but first of all, let's find out magnetic field because of these wires. So again, put your thumb over here and see that at the top, how is the magnetic field? Magnetic field is out like this. And here magnetic field is like this. What about this? Here also it will be in this direction. Here also it will be in this direction. Okay, so let's write Ampere's law. So we are going to write over here B dot dl. Okay, that's from A to B. Same way B dot dl from B to C plus B dot dl from C to D, then B dot dl D to A equal to mu naught I inside. Now how much is I inside? We have to decide that what is the length of the loop we have taken. How much bigger is our loop? Okay, because L is the length of the sheet. This is L. Okay, no, not this. This is L. This is given to you here. Okay, we have not taken what is this. So let's take this as dl. Okay, so mu naught. Now I want what I want. How many number of turns are there in dl length? So what to do? Already it is given to us that there are n number of wires in L length of wire. Okay, this is given. So n is equal to what? Number of turns into length of sheet. But how much sheet we are taking here? dl. So what will come? come as dn. dn will be equal to n into dl. So this is what we want. These are the number of turns which are there in loop. So let's write over here n into dl and then into I. Normally in the case of sheet, it will be giving you k. K is used as number of wires per unit length. So in place of this n, you will be using k. Okay, fine. So here what now? We can see clearly B dot dl AB. Okay, this AB. In this one, magnetic field is in this direction and dl is in this direction. That means angle between B and dl is 90 degrees. So here magnetic field or the dot product of them is 0. Okay, next one, BC. Now BC here and magnetic field is in same direction. So we'll write it as it is, BDL. Okay, plus CD. So CD is also in this direction, but magnetic field is like this. So magnetic field is perpendicular to CD, again 0. Here you are coming from D to A and magnetic field is also in this direction only, same direction. So we'll write this as BDL equal to mu naught NDL into I. So what you got here, you are getting 2 BDL equal to mu naught N dl into I. So dl and dl gets cancelled. Magnetic field comes out to be mu naught Ni by 2. Mu naught Ni by 2. This is important. You should be able to use this Ampere's loop. Okay. So this is mu naught Ni by 2. One more thing. In solenoid also. In solenoid, if you see, we said that magnetic field throughout the axis of the solenoid is constant, uniform, and its value is mu naught Ni. But here and here, magnetic field is not mu naught Ni. It is mu naught Ni by 2. Just remember that. Here is mu naught Ni by 2 and here also it's mu naught Ni by 2. Remaining everywhere inside this solenoid is mu naught Ni. Only at the end, magnetic field suddenly decreases to half. Remember that. Okay. Now, there is one special case of solenoid. We call it as toroid. Toroid is what? If we are going to turn the solenoid into a circular way. Okay. So, what we are getting is a toroid. Toroid is how? Toroid is like this. Okay. So, something like this is toroid. So, bring it here. Okay, something like this is toroid, and then there are turns in this one. I am not making that many, I am just showing you. Okay, 1 or 2 I will be showing, that's all. Like this, there are turns in this one. So you can say it's basically a circular solenoid. This is circular solenoid. Okay, so where we found, where we saw the magnetic field of solenoid is there along its axis. So where is its axis? Its axis is also here only. Okay. What happened? Okay. Its axis is there in the middle. Okay. Here. Like this. Okay. This is its axis. So magnetic field that we are going to get, it will be along the axis only here. Right? Here. Magnetic field will be found in this one. And how much is magnetic field? What will be magnetic field in this case? Now, we all know that the magnetic field that we found in solenoid's case was mu naught Ni. Okay. And I is current. Here is also current is I. So mu naught Ni. Now N is what? Number of turns per unit length. So in this one we will say, okay, if number of turns are N, then total length of the solenoid is what? 2 pi r into I. So this is magnetic field found in toroid's case. In toroid, it will be given to you how many number of turns are there, what is the effective radius of that one, that will be given. Then we can find this is the magnetic field along the axis of the toroid. What is magnetic field here? Magnetic field here is 0. Here 0. So magnetic field is only along this white line that I have made, or white ring that I have made, because that belongs to the axis of this toroid. Okay, so this is toroid's case. What type of questions we expect? Normally, as I told you, that one question will be at the end of the solenoid, what kind of magnetic field is there? Half, mu naught n I by 2. Then there will certain questions will be there, number of turns is reduced to half, radius is increased to double, then what will happen to the magnetic field? Okay, current is decreased to half, number of turns is increased to four times, or 1 by 4 times. Those kind of questions will be asked in solenoid. Okay, let's move ahead then. Then what we have? Right. So now we have is force on current carrying conductor. Now if a current carrying conductor we are keeping in magnetic field, there will be force on that. And what that force is? We write that force is I dl cross B. Okay, from where this formula came? This formula came from another formula that we studied, that there is a force on moving charge. Okay, it is derived from here only. So F is equal to I dl cross B. Now I is current and L is what? Length of the pipe, section, length of the section of a pipe, and B is magnetic field. Okay, so like that force, here also this force will be perpendicular to magnetic field, and this force will also be perpendicular to I, because first product here is ideal and there is B. So it will be perpendicular to this also, and it will be perpendicular to this also. Okay, so then how to find it? Suppose that we are going to make certain sections to know that how to use this formula. Okay, alright, we'll make it first. Suppose it's like this. This is the wire which is carrying current I. Okay, and there is magnetic field which is inside. Right, and the length or radius you say. Okay, radius of this is R. Then what will be the force and what will be the direction of the force? Okay, so what you will say that current is moving from here to here, true, but current is also associated with length, and it's a vector. So vector it is means this direction will always be from initial point to final point. Okay, so I require this. And how much is this? This is 2R, we know that. So it is diameter. Okay, so if I have to write the force in this one, the force will be actually B I into 2R. Okay, B I, and length what I have taken? 2R. And the direction is also this, not this. This is the direction, because it's moving from here to here. Now the question is, where is the direction of the force? What is the direction of the force? So here what it is? I dl cross B. So first arrange your hand in the direction of I dl. Where it is? This is. Curl your fingers in the direction of B. So where is the thumb? Upwards. So force is upwards. Like this is the force. Okay, this is force. Now same way, if suppose some another section we are taking, in that one you try to find it. Or if I take one ring over here, in the ring I want to find the force. Okay, current is like this. Alright, and magnetic field is inside here. Then what is the force on this? On this one force will become 0. On this one force is 0. Why? Because current is going and returning back to the same place. So if you are talking about displacement vector or length vector is 0. So that's why force is 0. Another way also is there in which we can see, if suppose we are going to break it into two parts, one is this one, another one is this one. Okay, the upper part, if you talk about upper part, you already have found the force is acting upwards. Okay, now let's talk about the lower part. When you find the lower part, its force will be acting downwards. So net force is 0. Right. One more. One more we do. And in that one, okay, fine. In that one, what you'll do is I'll be taking something like this. Sine wave we'll make. Okay, like this is the current going. Now in this case, what will be the magnetic force? Okay, so in this case, we are going to take the length as what? From here to join the final point. Okay, this is the length. This is your DL. Okay, so if suppose this is a circular track, okay. If it's a circular track and this is given as radius R, then you know that this is also 2R and this will also be 2R. Okay, so force on this one then will be given as what? Force on this one will give as BI into 4R. Okay, we say that magnetic field is inside here. So it will become BI into 4R. Clear? Okay. This is how we will find force on current carrying conductor and its direction. Okay. Force between two current carrying elements. This is important. Questions are asked on this one. Okay. So what it is? Two current carrying wires we will be taking. Okay. So two current carrying wires are here. Like this. This one is carrying current I1. This one is carrying current I2. And separation between them is D. So what is the force between the two? Right. So we will say that because if there is a force on current carrying conductor only when it's in magnetic field. If it's not in magnetic field, where is the force? No force. So first this wire is going to produce magnetic field here. Okay, let's say B1. What is the direction? Inside. So here inside is B1. Okay, inside. Now if it's inside, now I know that there will be force on this wire. Okay, B is like this and I is like this. Correct. So what is the force formula? IDL cross B. So in the direction of I first, I put my finger. Where is the magnetic field? Inside. So inside is my palm or rather full hand. Okay. First in the direction of current, my thumb. Then the fingers in the direction of magnetic field. Then palm is going to show you the direction of the force. So here is the force. But what is the force? You should know its value. Okay. So F is actually B, B1, I2 and the length of this pipe. Say L. Okay. So then B1 is what? So mu naught I1 by 2 pi d. Mu naught I1 by 2 pi d. Considering its length is infinite, it's very long. Make it as infinite, okay? It is very long, like this, infinite. Okay. So then mu naught I1 by 2 pi d into I2 into L. So since it's infinite, we don't find it like this. We always say that force per unit length. So force per unit length, the formula comes out to be mu naught I1 I2 by 2 pi d. Okay, exactly same way, this wire is going to apply the force on this one. So because of this wire, here, where is the magnetic field? Say outside. Outside magnetic field. This is B2. Okay, so force on this one will be what? Force on this segment is B2 I1 in its length. Okay, now which direction is the force? I is upwards again. Where is magnetic field? Magnetic field is outside, like this. So where is the force? Force is in this way, like this. What is its value? Check. B2 is mu naught I2 by 2 pi d into I1 and here is force by length. So this value and this value are exactly same. Okay, so we say that if two parallel wires are carrying the current in same direction, they attract each other. This is action, this is reaction. as action reaction force, magnetic force. Okay. So when two parallel wires, when two parallel wires carry current in same direction, they attract each other. They attract each other. And vice versa. Vice versa means is if they are carrying current in opposite direction, they repel each other. Okay. So this formula also important for us. If you remember, good. Okay. Force by length is mu naught I1 I2 by 2 pi d. Mu naught I1 I2 by 2 pi d. Both have the same value. Okay. So no need to worry that what will be force on this and what will be force on this. Okay. Equal and opposite. Alright. Okay. Now let's see, some questions are there. This is a question on a solenoid, a simple question. Okay, what it is? Number of turns are 20 per centimeter. That means number of turns per unit length is given. Magnetic field is given 20 millitesla and is asking current in the solenoid. Very simple, right? B equal to mu naught Ni. B is 20 into 10 to the power minus 3. This is 4 pi into 10 to the power minus 7. Number of turns per unit is 20 turns per centimeter. Centimeter we should convert in meter. What shall we do? Divide with 100. Okay, then what? What else? Current we have to find. Okay, so what we are getting here? This is 4 pi into 10 to the power minus 5. This 100 went up, it became 10 to the power minus 5 into 20 into I equal to here 20 into 10 to the power minus 10. So 20 and 20 cancelled here. Okay, so I value is what? I value is coming 10 to the power 2 by 4 pi ampere. Okay, this is the value of current is coming. Okay, 10 to the power minus 3 by 10 to the power minus 5. We get 10 to the power 2 by 4 pi. Okay, so this is simple question. As I told you, most questions from the solenoid will come that number of turns is changed and radius is changed or current is changed, then what will happen to the magnetic field? Okay. Right. Let's see another one. So in this one, what is there? There is one wire which is carrying current I1 and there is one loop. In this one, current carrying is I2. He is asking find direction of force on rectangular frame. Now, what we can see is the direction of current in this one and direction of current in this one is same. So on this one, there will be attraction force. F1 you say. Okay. Now, same current is going to move in this direction. Now, what kind of force is there between this and this? Will there be force or not? Definitely force is there because this wire is producing magnetic field inside like this. This is the magnetic field. Inward. So inward is magnetic field. Current is like this here, I2. Okay. Will there be force on this one? Obviously. This is I2. This is magnetic field. So force is upwards. So on this one, definitely force is there. Let's say F1 dash you say. But exactly similar or equal force will be here. In this case also. Magnetic field is way down like this. So current is this way. Magnetic field is inside. Where is the force? Downwards. So this F1 dash and F1 dash cancel each other. One is upward, one is downwards. Here also force is there. Where is magnetic field? Inside. So on this one, where is the magnetic force? Current is down. Magnetic field is inside. Force is this side. So here force is this way. Now then F1 and F2 are going to cancel each other. Sir is no. F1 is greater than F2. Okay, because here separation between the two wires is less, whereas here separation between two wires is more. So because of that reason, F2 value will be less than F1. So question was asked from us in which direction find direction of force on rectangular frame. So that is towards left. So net force on rectangular frame is towards left. Net force on rectangular frame is towards left. Towards left. Okay, this is what this is. Now, if we can find this force, you already know mu naught I1 I2 by 2 pi d, that the distance. Here also same, between this wire and this wire we can find what is the force. Alright. Okay, let's see then what it is. Magnetic moment. Okay, what is magnetic moment then? Magnetic moment concept is very similar to dipole moment. Okay, but now we don't have permanent magnet in our syllabus, so we are not going to discuss about that thing. Okay, Q into 2L, what we saw in dipole moment. Here we are not going to talk about that. This magnetic moment is due to current carrying conductor. It's not because of permanent magnet. So this magnetic moment we talk as, it is basically I into A or Ni into A. What is N? N is number of turns in coil. Number of turns in coil. Current, we all know I is current. And what is A? A is area or surface area of the coil. Okay. Surface area of coil. So if suppose we have a ring, okay, it's carrying current. Its radius is R. So what will be its magnetic moment? We'll say I into pi r square. Okay. Magnetic moment is I into pi r square. Now what about the direction? What direction? And because area's direction I can take outside also, I can take inside also. In two-dimensional bodies, we can take area anywhere outside. It should be normal to the surface, but normal to the surface can be inside also, outside also. Then which way you should take? Which one we should consider? Then we should consider it in which direction this is going to produce magnetic field at the center. Magnetic field produced at the center is inside. Okay, so area also will be inside only. Okay, inside vector will be considering as area. So in this case, if I have to write, this is actually minus k. Okay, so here in this case, remember area vector is in same direction as magnetic field produced by current carrying coil, not external magnetic field, because questions will be coming in external magnetic field. You should not take external magnetic field's direction. Okay, so A is in same direction as magnetic field produced by the same coil. This is important point. Okay, this point is important. Okay, so here what we have taken? We have taken area as minus k. Same way we can change the orientation of the coil. Definitely we can change. Suppose it's like this. Okay, to change the orientation. Okay, change the orientation also, and let's make it size also. Okay, size also we'll try to decrease. Something like this it is. Correct. But still, any changes there? No. Still we are going to take its area as depending on how the magnetic field is. If suppose that this is anti-clockwise, so area vector will be taking as outside, because magnetic field will be produced outside only. So in this case, magnetic moment will be writing as I into pi r square into k cap. So nothing much of a difference in anything. Correct. This is, what is this? This is magnetic moment. If number of turns are more, then magnetic moment also is more, because Each turn is going to produce its own effect on that one, on magnetic moment. One is producing I into pi r square, so 2 will be producing 2 into I into pi r square. So it will become NIA. That's what I have written over here. What is the unit of this one? Ampere meter square. And it is a vector quantity. Magnetic moment is a vector quantity. Okay. Right. Then what we have? Torque on a current carrying loop. Okay. If there is a current carrying loop in the magnetic field, there used to be torque on that. So if this is a current carrying loop, okay, we are taking it as a rectangle. Right. And suppose magnetic field is like this. Okay. This is the magnetic field. And there is current like this here. And take it as PQ RS. Okay, PQRS. And current is moving in this way. So when the current is like this one in a magnetic field which is this way, and length of this loop, okay, length of this loop, how much shall we take? L. Okay, suppose this is L. Okay, the length we are taking is L. Right, the length is L. Now what? You can see that where is the force acting on this wire? So I is upwards, that is ideal, and where is magnetic field? Like this. So where is the force? Force is acting on this is inside. So on this section, on this wire alone, force is inside. What about this section? Here force is 0. Why? Because in this one I and magnetic field are in same direction. What is the force? Ideal cross B. Ideal B sine theta. Okay, if DL and B are in same direction, then force will become 0. Force is ideal B sine theta. And theta is what? Angle between I and B. Angle between current and magnetic field. And here current and magnetic field are in same direction. So force here is 0. Now on this one, here current is downwards I. Okay, magnetic field is like this. So what you will do? Again, current downwards, magnetic field is like this. Where is my palm? Outside. So on this wire, force is acting outside like this. Okay, then again on this one, force is again 0. So here force is there which is acting inside, here force is there which is acting outside. So what will happen to this? If suppose this is pen over here, on this side the force is inside, on this one force is outside. So how it will do? It will turn. It will turn. So there is a torque on that one. Okay, there is a torque. Now torque about what? Torque about an axis. We can say that it's passing through its center like this. Okay, you can say that this is axis of rotation here. Okay, so what you will do? What is torque? Torque is R cross F. What is R over here? This is R. Okay, so let's say this is R and this is also R. Okay, so torque is equal to R cross F. Now what is the angle between R and F? 90 degrees. So I'll say torque is RF, which is produced by this force. What about this force? This is also RF. So shall I add or subtract? I need to add. Why? Because both are producing the torque in same direction. Okay, this force here is acting outside. So outside means is how it is trying to turn it in this way. Okay, and here it is acting inside. So how it is trying to take turn like this. So torque effect is in same direction. So what you will do? We'll add it. So R into F plus R into F. So what this is? 2R into F. Now 2R is basically what? Length. Length of this one. Length of this segment. Okay, so we'll say that. Okay, fine. 2R into F. Okay, let it be 2R into F at the moment. Now what is F? That also we should write now. F is I dl B. So what is I? I is I only. What is length? This is length because this force is acting on this segment of wire. So this is L. And then D. Now this 2R into L is what? L into 2R. It's the area of this segment, area of this loop. Okay. So what it became? I, 2R into L became area, and this is B. Now what is I? I is actually magnetic moment. Okay. So torque is basically M cross B. M cross B. What is B? B is magnetic field, this external magnetic field. M, magnetic moment of this. Now you'll say that what is the direction of magnetic moment? You see that because of this current in the loop, where is the direction of magnetic field? Not external, not external. Because of this, where is the direction of magnetic field? Inside. Inside. So magnetic moment is also inside. IA into minus. That's magnetic moment. I into A. I into A is this 2R into L. 2R into L into I. That's magnetic moment. Okay, what is the direction? Inside. Remember that. So torque is equal to M cross P. Whenever you are keeping one current carrying loop in the magnetic field, there will be torque acting on it. Okay, that will be M cross P. Now, depends on directions. If suppose M and B are in same direction, so obviously there is no torque. But if M and B is making any other angle, there will be definitely torque on that. Okay, fine. So where is the use of this? The main use is in moving coil galvanometer. Same galvanometer that we are using in current electricity. Okay, so what this moving coil galvanometer is actually? The moving coil galvanometer is, in this one coil is there on which there are number of turns are there. So when you use number of turns, okay, if you use number of turns, then what happens to the torque or to the magnetic moment? Magnetic moment becomes NIA. The torque also becomes NIAV. So more number of turns in the coil, more will be the torque on that. Okay. So what we are doing in moving coil galvanometer, we are using number of turns. So that torque on that becomes NIAV. Okay. And in moving coil galvanometer, external magnetic field is produced by this kind of a magnet. Okay. Why like this one? Because it produces radial magnetic field. That means magnetic field will be radial, direction of radius. Okay. So it's like this. And one more I'll make. Okay. It will be like this. And one more I'll show you like this. And this is how the direction of magnetic field is. If this is N to S, so direction will be obviously this one. And here will be coil. Okay, this coil is going to rotate. Okay, this coil is going to rotate. Now when this coil rotates, because of the torque obviously, in whichever case, however it is, in whichever orientation it is, remember its magnetic moment is always perpendicular to magnetic field. Okay, radial magnetic field, why we are keeping over here? So that its magnetic moment is always perpendicular to magnetic field. So that torque is always maximum. Torque is always maximum. Okay. Area of coil is always perpendicular to magnetic field. Perpendicular to magnetic field. Okay, so torque is constant. What is that? NIAV, always. We never talk about sine theta or something in that one. Torque is NIAV. Okay, then what happens? Now when the torque is acting, obviously this will be rotating. Okay, then how galvanometer will give us reading? Because that deflector has to stop somewhere. So we will stop it by applying one spring over here. The spring is here. Okay, the spring will be connecting. How the spring will be? That will be coil spring. Okay, coil spring will be here. Coil spring will be used. So as it is rotating, it will twist the coil. The twist the coil is done. Once you twist the coil, spring is going to resist it. Okay. So when the torque in that one or restoration torque in spring becomes equal to NIAB, it will stop. So restoration torque in spring we write as C theta. It is proportional to how much you are going to twist it. More the twist you give, more will be this torque. Okay. More will be this torque. So then in the equilibrium, we are going to equate both. So NIAB equal to sin C theta. And what is this C? C is torsion constant. C is torsion constant. Okay. Now what? We want our galvanometer to be very sensitive. Even smallest amount of current is there, it should be giving enough deflection so that we can identify. If suppose that 0.1 ampere is giving and it hardly deflects, it's towards zero only because current is small, so deflection is small. So we will not be able to find out that current has passed through that. Okay, and galvanometer basically is used for what? It's used to detect the current. Detect the current or to measure small amount of current. Small amount of current. Okay, it cannot measure large amount of current. Why? I will tell you that. But at the moment, it is to detect the current and to measure small amount of current. Okay, fine. So what we have got NIAB equal to C theta. Now, as I said that, what we want in this one? We want that it should give us enough value of theta, right? Even for small value of current. So we define that as current sensitivity. Our galvanometer needs to be current sensitive. Current sensitivity is what? Okay, here is a meter. Fine. So what is current sensitivity? Current sensitivity. Okay, that is actually theta by I. Deflection produced per unit current. So what it is? Theta by I. Theta by I will go NAB by C. Okay, so we can increase current sensitivity by making more number of turns, more area, more magnetic field, or by decreasing torsion constant here. Okay. Then another sensitivity is also there. Voltage sensitivity. Why this current sensitivity and voltage sensitivity? Because we are going to use this galvanometer as a meter and voltmeter. Okay. So voltage sensitivity is what now? Now voltage sensitivity, from where it will come? Because in the formula there is no V. Okay, where is V in this? So we have to bring V. So what we will do in place of I will be writing as V by R. Okay, now it came. So voltage sensitivity will be what? Sensitivity will be what? Theta by V. Deflection produced per unit change in voltage. Theta by V. Theta by V will be what? Theta, and this V is going there, and C will be coming here. So NAV by NAB by RC. This is voltage sensitivity. Okay, fine. Now, if number of turns, if I am going to increase, current sensitivity is going to increase, but voltage sensitivity will decrease. No, voltage sensitivity will remain same. Why? Because number of turns if you are adding, that means number of coils you are increasing. If number of coils you increase, resistance also will increase, no? Resistance for current also will increase. So here is N by R. So if N increases, R also increases. So voltage sensitivity, there will be no change, but current sensitivity will increase if you are increasing N. Okay. If you increase area, both will increase. If you increase magnetic field, both will increase. If you decrease C, both will increase. But with the number of turns, if you are increasing, current sensitivity increases, but voltage sensitivity remains same. Okay. Now this is how galvanometer works. So there can be question directly on this one from you, or maybe how the current sensitivity is increased, number of turns increase, area increase, this, that ratio, both current sensitivity and voltage sensitivity. Okay, that kind of questions will be asked. So ammeter now. Now what ammeter is? Ammeter is a device through which we want to measure current and large amount of current also. Okay. Used to measure current. Okay, and we are making this ammeter from galvanometer, but we said that galvanometer cannot measure large amount of current. Reason? What was the reason for that? The reason is, if we are going to have large amount of current in the galvanometer, in this one, so there will be more torque also. Correct? More torque is there or higher torque is there, then it can break our spring also. Right? It can break our spring. Second thing is, if suppose it's not able to break the spring, but then theta also will increase. If C, because C we have to keep up to certain extent only, we cannot make a big spring which has very high spring constant. Okay, so it is of certain value only. So if we are going to make more current into that one, then theta also has to be more. But galvanometer size is very small. It can break it. Right. So that's why galvanometer is used only to measure small current. We can allow only small current to go inside. We cannot allow large value of current to go inside. So then how to make ammeter out of that? How to make sure that galvanometer is not broken? So what we do is, we take galvanometer, okay, and but we connect one resistance here, small resistance in parallel. We call this a shunt. Okay, its resistance is S, and this S is small as compared to resistance of galvanometer. Okay, resistance of shunt is very small as compared to resistance of the galvanometer. So what happens then? Then when current comes from here, large value of current, this is a junction. So in this junction what will happen? Current is going to split. Okay, the current which goes into galvanometer, we say that this is full scale deflection current for galvanometer. We represent this with Ig. What is Ig? Full scale deflection current. Full scale deflection current. Because ultimately this only has to deflect. Galvanometer only is having the deflector. Okay, through that only we are going to get the reading. So here goes Ig only. Then remaining goes here. Since resistance of shunt is very less, then I minus Ig's magnitude will obviously be more than Ig. Okay, because they are connected parallel, so potential has to be same now. Ig into G will be equal to I minus Ig into S. S being very small, then I minus Ig has to be greater than Ig. So maximum current passes through shunt, very small passes through galvanometer. Okay, and whatever passes through galvanometer, that only produces the deflection. Because maximum deflection is fixed. Whatever maximum deflection in galvanometer, same deflection will be there in ammeter also. Okay, but then how ammeter and galvanometer scale will be different? Galvanometer can give only up to, let's say, a 0.1 ampere only it measures, but ammeter is able to measure up to 100 amperes. Only scale will change. Okay, dial will be same, because ammeter is not that sensitive like galvanometer. Okay, so ammeter we will be using for measuring of larger values only. So if ammeter or rather galvanometer is giving you deflection of 0.01 ampere, ammeter will not show that, because its scale will start from the higher value, 1 ampere and all that. Okay, fine. So now this is the case. So now what they ask you, what question they will ask? What should be the shunt value? So very simple. Potential in this one and potential in this one is same. So what you will say? Ig into G equal to I minus Ig into S. What is S value? Ig into G by I minus Ig. That's S. Simple. Simple question. Okay. Now suppose We make a question over here. Okay, question says that you want to make ammeter which can measure 5 ampere current. Okay, so 5 ampere current is here, right? And here is we are making galvanometer, and here is your shunt. Okay, it's like this. Okay, a galvanometer's resistance. This I is given to us as 5 ampere. Okay, galvanometer resistance you can say is 50 ohm. Okay, and full scale deflection current, that's a 0.5 ampere. Okay, you cannot allow more than 0.5 ampere to go inside. Okay, now it's asked from us that what is S value? How can we make this galvanometer to work and measure 5 ampere current? Okay, for that what shunt is required to be added? Where shunt is to be added? Parallel. So what is its value? We know now the formula, but even if we do not know the formula, we know what to do. Ig into G by I minus Ig. Ig is what? Says 0.5. 0.5. Resistance of galvanometer 50. Then here is 5 minus 0.5. Okay, so this is 25 by 4.5. This is the value of shunt. Okay, that's all. So these kinds of questions will be asked from you as far as ammeter is concerned. Same way voltmeter also is there. Voltmeter is also constructed from galvanometer only. And galvanometer, in voltmeter's case, what it has to do? It has to measure potential difference between 2 points. Used to measure potential difference between 2 points. Between 2 points. Where it is connected? Ammeter is connected in series always. Now on that also there are questions. One diagram is made, they have to identify where ammeter and voltmeter are connected properly. Ammeter is always connected in series and voltmeter is always connected in parallel with the resistance. Voltmeter is connected in parallel with the resistance. Ammeter is connected in series with the resistance. This is how ammeter is connected. And this is how voltmeter is connected. Okay, voltmeter is always parallel because you have to find potential difference between 2 points. So you have to connect voltmeter between those 2 points. So it becomes parallel. Ammeter, you want to measure the current, whatever current is going in this resistor, you want to measure it, so it has to be in series. Clear? What happens here? Okay, so this one is the ammeter and voltmeter, right? But we are actually trying to study voltmeter first. So how voltmeter is made? So galvanometer is here. Okay, in series to this, we connect very high resistance, R1. Okay, this R1 is a lot more than G. R1 is a lot more than G. Because of this, what happens? Now, what we did was, this was actually the circuit. Okay, this is the circuit actually. Now, what we did is, we connected this voltmeter in parallel with this resistor. Right, we want to measure potential difference between these 2 points which are A. So, from this battery, current went like this. So, here itself, there is, what is this? This is split here, current split. So, here goes what? Ig, and here goes I minus. Parallel, so whatever potential I minus Ig current is producing across this, same potential Ig will produce across this. So what we made sure is, by resistance we increase over here, so that very less amount of current goes in galvanometer, because you have to make sure that galvanometer is safe. So Ig only is going. So this time what has happened? I G into R plus G or R1 plus G rather. Because total resistance of now voltmeter is what? R1 plus G. And what current is going? Ig. So Ig into R1 plus G is equal to what? I minus Ig into R. Normally we will not use this because question will say that we want to make a voltmeter which can measure up to 10 volt. So this is actually 10 volt. This will be given 10 volt. And they will be asking you what should be R1 for that. Galvanometer resistance will be given, Ig will be given. Okay. One question we will frame. Okay. See. To make a voltmeter, that can measure 50 volt. Okay, galvanometer of resistance 10 ohm. Resistance 10 ohm is used. Full scale deflection current. Full scale deflection current is 0.1 ampere. Find what resistance is connected in series with galvanometer. In series with galvanometer for this purpose. Okay, for this. Here is the question. Very simple actually. Right? What we have to do? Okay, we know that Ig into G plus R1. This is what the potential across galvanometer is. And this should be equal to what? He says 50 volt. Okay, this is given 0.1, G is given 10, this is R1, this is 50. So this is 500, so R1 is 490. That's all, finished. These types of questions will be asked from you in voltmeter, ammeter, voltmeter. There will be questions. Okay, there will be questions. So, including this all, this chapter will have maximum 3 questions. Okay. Alright. Then what we have? Work done in rotating a loop. Now, when we know that when we kept one coil, current carrying coil and magnetic field, there was a torque on that. So, work done in rotating the torque is what? We saw that in dipole. Okay, exactly same. Because a current carrying coil here is becoming a magnet and it is having magnetic moment. Okay, and there is a torque M cross B in that one. So, very similar to what we saw in dipole. So, same way, work done is what? In rotating. Work done in rotating we calculate as tau d theta. Okay, tau d theta. Like work done with the force we call as F dx. Same way, work done in rotating we call as tau d theta. Okay. So, this is tau d theta here. Now, tau is what? Tau is mb sin theta. So, you can say this is mb sin theta. And this is d theta. So, m and b is constant. So, it becomes sin theta d theta. From where to where you are rotating? So, from theta 1 to theta 2. So, we will integrate it. What is integration of sin theta? Say minus cos theta. Okay. So, minus cos theta is here. Right. So, what we will write here is mb minus cos theta, and here comes theta 1 to theta 2. That's all. So, mb cos theta 1 minus cos theta. Remember this. Though there were questions on this one in previous years, but this also is removed from our syllabus. That's why in dipole also I don't think we studied rotation. Okay, we didn't talk about rotation in dipole also. So here also we are restricting ourselves to only how much work is done to in rotating the dipole. Okay. So we saw this one. Now what next? What is next over here? Electromagnetic induction. So I'm not starting it right now. Okay, we'll see this tomorrow. Tomorrow will be your long class. So be ready for that. Maybe 2.5 to 3 hours class in a stretch we are going to do. Okay. So that electromagnetic induction is over tomorrow, and I can have a small introduction of AC, or maybe we can be going to a certain length in AC. Okay, so we are closing here and not going forward in electromagnetic induction as such at the moment. Okay, so scan this one for the notes so that you can just go through it when we are revising it just before the exam. Okay.
Yes.
Yeah, let's scan it. Done?
Yes.
Okay, students, then see you tomorrow. Bye bye.